Welcome back, everyone. We'll get started in just a few more minutes. Welcome back, everyone, to the discussion section of today's Capra meeting. People are still streaming in, so we'll maybe wait a minute or so. Today's discussion session will be focused on second-order self-force and will be led by Adam Pound. So, Adam, you already have co-host privileges, so if you'd like to start your screen share, feel free.
Okay, thanks.
So big thanks to Adam for agreeing to chair this discussion, even after giving a talk this morning. I'm sure more people will come in, but we seem to have stabilized for just the instant. So Adam, why don't you start whenever you're ready?
Okay, thanks, Aaron. So I've split this up into four sections, very similar to what Niels did. I'll start with just a rundown of the current status, and then have a few different topics for discussion. So The obvious topic is second order self-force in Kerr spacetime. And I think there's a preliminary topic that needs to be addressed before we can even really do that, which is how to get a good first order metric to put into the second order field equation. Then second topic will be post-adiabatic evolution of the Carter constant. So we heard about balance laws for energy and angular momentum, but we don't have something equivalent for the Carter constant. And then the last topic will be returning to the topic from yesterday, which is how do we fill the huge parameter space? And what I'll do is when we move from one topic to the next, I'll just announce that in the Slack so that if people want to skip one session, one topic, and just wait for another one, they can join when we start the other one. Okay, so current status. Let's see if I can move this out of the way. As usual, I gave myself way too much to cover this morning, so I was really rushing through the material and probably didn't really convey what the current status is. So currently, the calculations that I'm doing with Barry and Niels and Jeremy, we can calculate any mode of the second order field for quasi-circular end spirals and Schwarzschild. We have calculated modes up to L equals 5, L equals 5. We are still missing some stuff in our calculations. We have complete stuff at for some data points, but not for other radii. So one of the things I pointed out that goes into the field equation is a derivative of the first order metric with respect to an orbital parameter, in this case, the orbital radius. And we only have this for a few orbital radii. We haven't filled out the parameter space for that yet. We're doing something really crude right now. We know we need a puncture at the horizon, but we're basically just chopping off the integral instead. So that needs to be worked out. And I showed those nice results for the flux. The results look great for every mode except 2. The 2-2 mode is the worst behaved. It doesn't match the predictable. I suspect that's something to do with the choice of reference frame. It's somehow connected to the first order 1-1 mode, which tells you what center of mass is. And what was the other mode that wasn't working well? Niels, help me out here.
I don't know off the top of my head, but I'll post it in the chat in a second.
It might be the 3-1. I don't remember. Anyway, that one's better. It's really the 2-2 that's wildly wrong. I mean, it's still falling off with radius, but not at the correct power law. So yeah, so some quantities are still misbehaving. We have a lot of checks to do, a lot to iron out. There's just a lot of moving parts to the calculation, and we need to go through each one and check everything. Okay, so that's the status of our calculations. Now, why are these calculations so challenging? Why are they taking us so long to do? We've encountered 2 main problems, both of which we've overcome, but maybe not in the optimal way. So the first challenge we faced was this problem of having to add up an infinite sum of first order modes. So this is a plot from a paper with Jeremy Miller and Barry Wardell, where we were looking at a scalar toy model, but it's exactly the same behavior in the real thing. So this is a mode of the second order source that we're trying to reproduce, or we're trying to calculate, and we're trying to calculate it by adding up products of first order modes. So we express each mode of the second order source in terms of products of first order modes, and then we add them up. And you see, we're trying to reproduce something that's infinite, and so the more we add, just the higher we go, and it never converges to anything. So in this toy model, we could add thousands of modes because we had them analytically, and yeah, it just you never have enough. So the way we overcame this works, but it's extremely computationally expensive. So what we did was we split the second order source into a collection of different terms. So we wrote H1 as a puncture plus a residual field. And then the second order source has a term that's puncture times puncture. It has a term that's puncture times residual field times puncture, and residual field times residual field. And then we calculated this first term, which is the term that is that we can't replicate with the sum. We compute this by putting in a three-dimensional puncture. So we start with the quasi-local form of the puncture. We calculate the three-dimensional source, and then we integrate that against spherical harmonics to get the modes of the source. Then all the other pieces, the puncture times residual and residual times residual, those we can use just the sums over modes. And in fact, we have to, because we don't have the residual field as a three-dimensional field. We only have it as modes. So this works. Here's a demonstration of it working. The blue curve is the result of this method. And we can check, for example, that the second order puncture exactly cancels this source. The black curve is the attempt to reproduce that by adding up a whole bunch of first order modes, and it is failing to do so.
Now, you mentioned that this was really expensive to do. Why is this particularly expensive? Are the actual integrals over the puncture have to be computed numerically on the fly, or what's going on?
Nothing's computed on the fly. Everything's pre-computed and stored. But yeah, they're evaluated numerically. And what makes this so expensive is that you put in a three-dimensional puncture here, but then you put in modes of that exact same puncture here and here. And you have to make sure that that is exact. This is an exact mode of precisely what you're putting in here. That's not normally what you do when you're doing these kinds of integrals. Normally you make use of re-expansions and simplifications of the integral. That's impossible here because we don't add up to the correct thing if we approximate different terms here differently. They have to exactly correspond to each other. And so what that means is we have to take this three-dimensional puncture and get its modes by evaluating these numerical integrals on a grid. In that case, Barry will correct me if I'm wrong. Hopefully he's on the call. In that case, I think it's just a 1D integral done numerically and the other one's done analytically. But nevertheless, it's extremely expensive. You need to calculate these on a pretty dense grid because this is where things are changing rapidly. And so we usually have about this wide a space around the particle, a width of around 4. And this calculation takes 99.99% of our computation time.
Okay.
I think in fairness, there's a lot of room for optimization. I mean, it's a mathematical implementation. Yeah. It's the first pass that we're doing these things. So I'm sure you could squeeze a factor of 10 to 100 easily, but it's still very expensive. That's definitely true.
Even a factor of 100 is still going to be slow. It's really slow. This is not calculating that many modes compared to what we'll have for eccentric orbits. So this is a real bottleneck in terms of computation time. So we're trying to come up with methods of improving that. So an obvious method is just to optimize the integration routines, just optimize the numerical methods. We're also trying more fundamental ways of improving the behavior. So one is to use this highly regular gauge that Sam Upton was describing today. And how do I respond to Jordan?
You can just call on him and he'll talk.
Okay, Jordan, go ahead.
Sorry, I have a naive question. So if a significant part of this problem is a very large sum over modes, can some of that not be assisted by using a pseudo-spectral method, in the sense that you would, for instance, choose collocation points or collocation points on a sphere, and then compute the nonlinear terms by products of those collocation points?
Could be.
Well, Adam, you mentioned this is reduced to one-dimensional integrals, so presumably the angular pieces have already been reduced in that manner.
Yeah, so Barry is always hoping to do even this integral of the product analytically in one angle and then numerically in another one. But so far he's always resorted to two-dimensional integral. But then for the modes of the puncture, yeah, there I think he does a one-dimensional integral.
Okay, then I guess I'm wrong and Jordan's point stands.
Yeah, to clarify, so is it the case that what is currently being done is the direct sum over L's such that the L's sum appropriately?
What do you mean by sum appropriately?
By which I mean, if you are looking for the L equals 2 mode, then you have a one-dimensional sum over L's for the quadratic contribution to that.
So the coupling
Right.
obeys, standard angular momentum coupling rules.
Right.
So it's
Okay.
triangle inequality.
Right. This is what I mean. So it's that sum that's being directly evaluated.
That's what's being evaluated in this and this and this, but not in this.
Okay. Yeah. Okay. Perhaps at some point we should talk about specifics about what I'm thinking of for the pseudo-spectral method, but those techniques are, generally speaking, considerably better behaved for computing nonlinear products of spectral modes.
Computing nonlinear products.
Which is to say, the point is, one way you can compute the product of two quantities that are both represented as modes, is to just sum the modes with the appropriate 3J symbols, for instance.
Mm-hmm.
But another way to do it is to actually perform the transform to well-defined collocation points for each of the quantities ahead of time. Now, not work directly with mode coefficients at all, instead work with field values at specific collocation points such that you maintain the spectral convergence. And then in these so-called pseudo-spectral methods, the computation of nonlinear quantities is completely direct and simple, because you have them on a spatial grid that maintains your spectral convergence. And you can just, on each of those grid points, you take the product. And then if you need the modes at any point, you then perform the forward transform.
So that sounds very promising, but I'm worried about when you say preserve the spectral convergence.
Right.
Because the whole problem is that these modes don't actually fall off quickly.
This is specifically in R.
In R?
Or in any, you mean these modes do not fall off quickly in any sense of
L.
the term? In L.
In
I see.
L.
yeah, that does make it challenging. But presumably, the problem is less bad for the H1s than for the H2s.
H1s and H2s.
Which is to say that is that poor fall-off behavior comparable for the starting point of the product as for the D2Gs that you compute at the end?
Good question. So the D2Gs, this will, yeah, it has like a very slow exponential decay. It's technically exponential, but very, very slow. And then it's going to be, what's it going to be? Where's Barry when I need him? I'm not actually sure what the L dependence of this is. All I know is the L dependence of the sum over this thing, sum over the products inside. Good question.
Leo points out a good point that the pseudospectral method may encounter problems given that you do have a singularity somewhere in the domain.
Yeah, so this is the entire cause of our problem. If we didn't have that, we could just go ahead and use the Clebsch-Gordons. So far away, the sum over products converges really quickly, really, really quickly.
I see.
It's just this singularity infecting everything around it.
Okay, thanks.
But yeah, that sounds like something to look into. So the other promising thing is something Chris Kavanagh will show tomorrow, where he's able to magically evaluate sums analytically, basically using MST. And so he gets closed form expressions for the infinite sums. So we need to test how accurate the MST approximation is, but it seems so far like pretty spectacular results he's got. Okay, so this is the main computational bottleneck. Now, the other problem we encountered was this breakdown at large distances. So the 2 timescale approximation breaks down far away from the system and as you approach the horizon. And the manifestation of that is that the source in your equations doesn't decay quickly enough as you go towards the boundaries, and then the retarded integral of it diverges. So the way we're getting around this is we are finding local time domain approximations, not 2 timescale approximations, near the horizon and near infinity, and then converting those into punctures for the 2 timescale numerics and solving for the residual remainder. So this is not too bad, but it requires a whole additional analytical calculation that's fairly complicated. One hope I have is that when we switch over to the Bondi-Sachs gauge, then, oh, there's Barry. When we switch over to the Bondi-Sachs gauge, like discussed in Andrew's talk, I have a sneaking suspicion that will make the 2 timescale expansion actually well behaved all the way up to infinity. So my suspicion of that is based on what I found really just for the monopole mode, that I could transform to a Bondi-Sachs gauge for the monopole mode, and then it actually smoothly extends all the way up to infinity, still within the timescale approximation. Okay, so these are the kind of big barriers we encountered. Now, the biggest barrier is really just there's so much stuff to do. So there's just so many moving parts in calculations. One thing I want to emphasize here is that as we've gone along, we keep having to improve the first order results and get more information from first order in order to do the second order stuff. So in order to calculate a mode of the second order field, we need a long laundry list of things from first order. We need the retarded field modes on a radial grid. We need the puncture field modes on a smaller radial grid near the particle. We need the derivative of the retarded field modes with respect to the orbital radius, also on a radial grid covering the entire space. We need the residual field summed up, so like the actual Detweiler-Whiting regular field, all of its components, and all of the derivatives of its components on the particle. We get contributions from the slowly varying mass and spin to basically every single thing. We need the first order self-force. We need the derivative of the first order self-force with respect to orbital radius. We need coefficients in large R and near horizon expansions of the first order retarded field. So we need a lot of information from first order. Second order, we also need a long list of things. We need punctures at both the boundaries. We need modes of many different types of punctures of the particle. We have a whole list of different types of integrals that Barry needs to evaluate. We need the modes of the second order source computed as a numerical integral near the particle, and also the sum of first order modes. And in some places, we also need to do an analytical expansion of it, particularly near the boundaries. So really, this is just a lack of manpower. There's just a lot of stuff to be done, which considerably slows things down because we're all doing lots of other things as well. But from the community's perspective, what I want to stress is that if you improve things at first order, you get better at getting things at first order, that will help second order because we need so much stuff from first order.
Adam, question?
Yeah.
Leaving aside the question of speed, is Martin's approach to the first order problem in the right form?
That will be the next topic. So that is
right.
the end of the summary of the current status and what the main challenges are just to complete the kinds of calculations that we're working on. Now, I said I would announce the new topic. How do I get over here? I said I would announce this topic in the Slack. Yeah, but we've realized that we need to go back to first order and fix it up in order to move on to second order and Kerr. Right back here.
Also, Niels has his hand up. Niels, are you addressing this particular point before we move forward?
I just want to say with the first order stuff, I think the thing that's just completely missing is the derivatives with respect to the orbital elements. So we have that in the Lorentz gauge for derivatives with respect to R0 with the metric perturbation everywhere. The other stuff I think is, we have these codes, or it's just a matter of running them and extracting the parameters and storing them. But I think the one that's really missing is that. So as we move to more complicated orbits, we'll need derivatives with respect to P and D and inclination. And I think that's, that's a more substantial project. If anyone's thinking, well, I'm not just so interested in just running things to more higher accuracy, maybe I won't get a paper out of that or something. I think there's a lot of useful. Yeah, we need that too. I'm not saying, but if you're looking at like the most interesting thing there, I think might be those derivatives with respect to the orbital elements. They're useful for second order. for the NIT calculations, we use them as well, which, as Adam mentions, all ties into second order as well. So if you're looking for something interesting at first order to do that would be very valuable, then that's something I would suggest.
Yeah, definitely. So we, Jeremy Miller and I, it was really Jeremy Miller who did all the work on that. And we have a paper draft that's not quite finished, but if anyone wants to get, get moving on calculations of those kinds of things, we're happy to share our paper draft with you to show you how we did it, which probably wasn't the best way, but it was a way that worked. And yeah, that's something that needs to be done. Eccentric orbits and in Kerr, and yeah, that'll be a whole new project on its own. Okay, so what I wanted to discuss here.
Actually, Adam,
Yeah.
Adam, can you hear me? Can I ask something about that? The derivative with respect to R naught. Is your way the one in which you take the derivative of the source and then you solve a field equation with the derivative of a delta function?
Yep.
All right.
In the frequency domain, we also get a derivative of the frequency.
Sure. Yeah. All right. Thanks.
But yeah, this was Leor originally suggested the method of doing that, so we're using his suggested method.
I don't even remember that.
It was,
just
it was many years ago now.
I was listening. It seemed to be like the natural thing to do, and I wasn't sure if that's the thing you were doing. So apparently, yeah. Okay. It's not the first time that it occurred to me. Thank you.
Okay, so yeah, the major barrier to going to Kerr now is exactly what Chuck was saying, that we've only got H1 in a particular form, and it is not a good form. So the H1 we have, courtesy of Martin in doing a full numerical calculation, or people doing MST, so Chris Kavanagh and Beanie et al. That metric we've got is in what we call a no-string gauge. So this is reconstructed in the radiation gauge, and then maybe add some completion bits to it. And the result is a metric perturbation that is singular on a sphere of Boyer-Lindquist radius equal to the particle's orbital radius at each instant. So it's a sphere that breathes in and out as the particle oscillates radially. So on that sphere, wrong way, on that sphere, we have a delta function. Oh, one of these is supposed to be a Heaviside function. We have a delta function and a Heaviside function. So say we try to substitute this metric perturbation into the second order Tucholsky source. As Andrew mentioned, at second order, the Tucholsky source is not gauge invariant. So if you have a bad gauge, you get a bad source. It's not like first order where Tucholsky is automatically gauge invariant, and so everything's nice. So say you put this metric perturbation into the source. The source is a derivative of the metric perturbation squared. So that gets you a delta prime squared, and then you hit it with two more derivatives. So this is really horribly ill-defined. This is not anything meaningful. So we need to get a better metric as a starting point for second order calculations in Kerr. I've just jotted down some ideas, although there's other ones I didn't mention for some reason. So one idea is start with the perturbation that we've got, and then somehow regularize it with a local gauge transformation that's just like in a shell around the sphere. So this goes back to discussions that Leor and I and Martin had years ago, but at the time we were wondering, do we need to really smooth out the metric a lot or completely? And for the calculations Martin was doing, we realized, no, we don't. We just need to smooth out very specific pieces. But going to second order, I think we need to smooth out everything. Another option would be to just get everything in the Lorentz gauge. So there'd be two ways to do that. One would be to directly solve the field equations in the Lorentz gauge using like a frequency decomposition and a azimuthal decomposition, but not maybe not a spherical harmonic decomposition. The other option would be to find a transformation from this no string radiation gauge to the Lorentz gauge. And I was hoping Sam Dolan would be on the call. Sam, are you around? I guess not. Yeah, so Sam had found ways of solving the electromagnetic wave equation in Kerr to get a Lorentz gauge solution. And that's actually what you need to do to transform to the Lorentz gauge. You need to find a gauge vector that satisfies a Maxwell equation with a source. And so I was actually wondering if we could apply his methods to find the gauge transformation. It's too bad that he's not here. Another option would be somehow use what we got, but regularize it in some rigorous way that guarantees that we get the same solution we would have got if we worked in a smooth gauge. Another option I didn't mention is work with a puncture scheme at first order. So only get the residual field in the radiation gauge, which is more smooth, and then leave the puncture in some other gauge. All right, so these are all just ideas. I think Peter Zimmerman will mention these again tomorrow. I don't know if he's on the call either. But any ideas for how to tackle this problem? Is Martin on the call? Is Chris
So
on?
Martin is not on the call. Sam is in the room, but he mentioned that he would be unlikely to be able to talk often because he's taking care of, I think, his kids. Peter, are you able to talk? Are you listening? Peter.
Yes, I'm here. Can you hear me?
Yes.
I am able to talk. I don't have any solutions yet to these problems.
You've
We've
had
been
a
talking
year.
about things recently, and to just kind of come up with the list that Adam's put down without making much headway on any of these topics. I think
Adam?
Sam Dolan's method for getting a vector fields in Kerr might be promising, because if you can get everything in Lorentz gauge, then, or a highly regular gauge from there, I think we'd be good to go.
Yeah, once we're in the once we're in the Lorentz gauge, it's easy to transform to the highly regular gauge.
Yeah.
Leanne has her hand up as well.
Leanne, go ahead.
Hi, Adam. Can you hear me okay?
Yeah.
Okay, I've been having some sound issues. So I don't know if you were in my talk yesterday, but just to briefly touch on your sort of second point there on everything in Lorentz gauge and getting that the potential vector for Kerr. So we think we might have a way of doing this in Schwarzschild, and while Barry will know a little bit more than me, when we get all this done in the sort of Newman-Penrose or GHP formalism, we believe it might be somewhat clearer how to get this in Kerr, that we might somehow be able to just spot it or see it. So that's work that we're doing at the moment.
Yeah, that seems very promising. When I talked to Sam briefly over email. He was wondering if the, what was that term? What was it? M something, AF something?
M2AF. Yeah.
Yeah, M2AF.
We
Yeah, he
need
was
a new-
wondering if that was related to something in his equations. I don't recall what though.
I'm not sure, but obviously his result as well is quite compelling for getting in that direction.
Yeah, yeah, I think it seems doable.
Yeah, it's work in progress, but I think, or we hope it will become clearer as we go, as with everything.
Yeah.
But yeah, stay tuned, I guess, for that.
Next Capra.
Yeah, maybe.
Adam, for the first option, the regularized local gauge transformation. So this would be mode by mode in the first order metric perturbation before putting it in the source and somehow matching on either side of the radius of the particle.
Yeah, so I think this would be really easy to do in Schwarzschild, but in Kerr, I can't see how to do it because each mode actually has a complicated angular dependence that doesn't factor out. Maybe Leo was thinking about this ages ago. Leo, do you have thoughts about this?
Yeah, so I think Leanne's method is the way to go, but I'll just remind that Sam actually wrote a 2+1 decode in Kerr, in Lorentz gauge, and that worked. We never wrote a paper about this. It wasn't very efficient, but it's something that somebody can, try to take on and develop. It is a possible approach. But there is actually a code, a Lorentz gauge code in Kerr. It belongs to Sam. It won't be the most efficient way.
And I think
that's what I wanted to
program again.
Sorry?
I think Sam also wants to never look at that program again.
Yeah, I know it's not nice to work on it, but neither is doing any of the other things you're doing in second order calculations. It's horrible. Yeah, that's one way to go. But is that the question you asked me, actually?
No.
Okay, what did you ask me?
About back in the day when we were talking about regularizing the no string gauge with a transformation, at the sphere.
Mm-hmm.
Do you remember if you had any good ideas how to do that in Kerr?
In a frequency domain framework?
Yeah.
I don't think I remember anything about that. Just you mean by doing a gauge transformation, so many.
Yeah, I mean, so in Schwarzschild or any spherically symmetric space,
In Schwarzschild, these are ODEs, yes, but in Kerr, I don't see them being ODEs. They're going to be.
Yeah, no, it'll be. Well, I think what it'll be is, so if you do a expansion near the sphere, you can reduce it to ODEs, but it'll be angular ODEs. Whereas in Schwarzschild, it'll be algebraic.
So you mean for Inc C, they're going to be ODEs?
Yeah, so expand C in distance from the sphere.
Oh, I see. I see. You remove the R dependence with an expansion.
Yeah, exactly.
Yeah, then you end up with ODEs, and I guess that's sufficient really for our purpose. Mm-hmm.
Is it even true though that if you reconstruct a radiation gauge metric perturbation on one side and on the other side in Kerr, should they actually be related by gauge transformation? I mean, should there be a gauge transformation that actually smooths them out on the sphere?
You mean between the two half
Between the two
string functions?
Yeah.
Well, here I do remember thinking about this, but I don't remember the answer.
Certainly, if you sum up all the modes, then obviously there has to be.
Yeah.
But mode by mode, is there?
Not clear. Not clear.
Adam?
Yep.
This is Chuck again. I just want to be clear as far as this regularization first point. The problem is over the entire sphere, right? Because there's a theta function. It's not just local in a local neighborhood around the instantaneous location of the small body.
Yeah, so this delta function is supported on the entire sphere. One of these is supposed to be a heavy side, one of them is supposed to be a delta.
So Adam, I think there isn't a gate. I mean, there is an actual source sitting there in the equation, in the action equations, right? So I don't think there's a gauge transformation between the two.
Yeah, because I think when you cross the sphere, you you have the source there, so you violate. You have the TLL condition that you violate, so you're not in a radiation gauge.
Mm-hmm.
You have to somehow glue it.
Oh no, I'm taking as a given that we've already done our calculation, Peter.
Ah, I see. Okay, yeah, then I don't know.
Yeah, so one thing that's potentially in advance over what we used to have is that with Martin's calculation, you wouldn't be able to tell you what the coefficient is of the delta function. Whereas now, now the work that Peter and I and Andrew and Stephen are doing, we think we can tell you what the coefficient is, even.
Barry, I'm going to go ahead and mute you.
Then you can figure out the gauge transformation uniquely.
Oh, are you telling me that you're able to calculate the delta there between the two no string gauges, half string gauges?
Yeah.
But that's precisely what Oli and I have been at pain to get.
I don't think we can do it in the time domain though.
Oh, I see. Mm-hmm.
Maybe,
Yeah,
I'm not sure.
Yeah, for Kerr, I can't imagine being able to do it in the time domain unless something real breakthrough happens.
Although maybe you could actually still extract the time domain one from the frequency domain one.
Well, so now we have a different method of getting them from the inversion relation. We can go backward and at least check your results.
Mm-hmm.
Okay. Go ahead.
Sorry. If we're finished with the particular question you had, I had a different question, but I can wait. Just quickly, where is it discussed somewhere, the particular Maxwell equation you get to generate the gauge transformation between radiation and Lorentz gauge? Or does one just derive it quickly?
Oh, it's just, yeah, anytime you're going from any gauge to the Lorentz gauge, the equation is that the box of the gauge vector is equal to the divergence, possibly minus the divergence, of the metric perturbation in the gauge that you're starting in.
Okay, yeah, I've got that written down, just checking. Okay, got it.
Some other paper on it, right? On this.
So he was doing this not in gravity, but I think he's solving the same equation.
Yeah, but I looked at the paper and there was some restriction in his assumptions about the type of perturbation for which this could be.
It might be
I
Hello.
forget exactly what it was.
Is Sam speaking now?
Yeah,
Sam?
sorry, I'm here. Am I able to speak?
Yep.
Yeah. So in that paper, it was specifically about Lorentz gauge vector potential without sources. And it looks a little problematic when you try to put a right-hand side in, because the reason that the method works in a rather mysterious way comes from some work by Frolov and his collaborators, and also a guy called Oleg Lunin. Anyway, for the separation to work, it has to satisfy the Lorentz gauge condition and the field equation. So div A equals 0 and box A equals 0. And the two turn out to be consistent when there's no source. And when there is a source, I can't see that the two are consistent anymore. So it's certainly not very straightforward to apply the method when there is a source, but it's worth thinking about.
So that sounds closely related to the fact that if you don't have a source, you can impose that a Lorentz gauge gravity solution is trace-free, but if you do have a source, you can't.
But do we need it with a source? If you can tell the jumps, the theta function there, then isn't it enough to apply this transformation in the two vacuums?
I don't think so, because the source is coming from the metric perturbation in radiation gauge, so it's extended.
Yeah.
We had the same problem, and we dealt with it with its corrector field, which we found to satisfy some nice ODE. So maybe it's possible there's some also corrector field formalism in this case as well in dealing with sources.
So I'm thinking about a no string kind of construction where you have two vacuums on the two sides, and you can apply transformation.
But the source in the equation is the divergence of the metric perturbations. It's not going to be 0 anywhere.
Source in Sam's equation?
In the equation we would need to solve.
Yeah. Sorry, can you say that again?
The equation we would need to solve for the gauge vector has a non-zero source everywhere, because it's just the divergence of the metric perturbation.
Mm-hmm. Oh, I see. Yes. Oh, so yes, got it now.
But it is interesting that if we are only interested in getting the trace-free piece of the metric perturbation, then that actually corresponds to imposing the Lorentz gauge condition on the gauge vector, that the divergence of the gauge vector is 0. And the trace part of the metric you can actually calculate directly in the Lorentz gauge, because it satisfies a separable wave equation.
Well, the trace part is just a Klein-Gordon field.
Exactly. So if you could get the trace-free part this way, and get the trace part that way.
Yeah, I think that's sort of what we were thinking in the UCD group. We haven't fleshed that out yet.
Okay.
Sam, since you're here, are you still here?
Yes.
Yeah. So we were mentioning your 2+1D code in Kerr, and you don't want anything to do with it anymore. But what do you think about the is it a promising thing for somebody to pursue?
Well, firstly, I'd be happy to hand it over in full to whoever wanted to try their hand with it. I guess there are two issues with it. The first is accuracy, because it was just a fourth order finite differencing on a grid. It may not give you the first order perturbation at the level of accuracy that you need to feed into second order sources. And the second issue is to do with the gauge mode instabilities. And I know Jonathan Thornburg has thought about this a lot, how to cure those linearly growing instabilities in the monopole and dipole sectors, which in Schwarzschild you can separate out, but in Kerr it's not so easily done. So those would be the notes of caution, but I'd be happy to give that code to anybody that wants to take it on.
So another technical problem is that for the 2 timescale expansion, we would then need to decompose the output of that code into frequency modes.
Sure, well, that shouldn't be a problem.
No? Okay. Can you just do a fast Fourier transform of it or something?
I would think so.
Yeah, then that sounds promising. If you can get it accurate enough near the particle.
I would think it would probably be more useful for checking other more efficient methods.
Hmm.
Yes.
Currently, we don't have any other method of generating a stage metric perturbation in Kerr.
I mean, give it to somebody who is keen and clever in numerics, and they can make something nice out of it. I mean, use hyperboloidal slicing and mesh refinement and all that. You can make it efficient, perhaps.
Perhaps it's already been discussed, but I know Barry and Chris had put quite some time into thinking about how to try to get a Lorentz gauge metric perturbation in vacuum by applying derivative operators to a kind of ansatz for a generalized Hertz potential. And they had found something that nearly works for a certain meaning of nearly.
Yeah, it was like the anti-trace world things or something like that.
Yeah, has that been reported on or taken further? I know Barry is.
I can talk briefly. I've got the.
Oh, Barry, well,
I'm listening in, but I'm not.
Congratulations.
I'll carry shoes at home. I think Leanne's talk pretty much covered a lot of the good progress that has been made. Namely, that it's kind of clear from Bernstein's work and from Leanne's follow-on of that what works, at least for Schwarzschild. It's not yet clear whether it will be completely separable in Kerr, but it's very promising that you just and you might be able to guess your way to Kerr from the Schwarzschild case reasonably easily. Would be the hope, although we haven't done that. But at least the Schwarzschild case, including with sources, is all there in Bernstein's thesis, essentially.
So, Barry, is there any connection between the M2AF term and, if you like, the blockage to success of your method?
That's a pure gauge piece as far as we can tell. So within the Lorentz gauge. So it's not clear if that's needed at all.
It's just an additive piece.
So, yeah. So I guess what I'm referring to is the S=2 piece. You can, in Bernstein, you can rewrite that in terms of Tchaikovsky scalars.
Yeah. And
that tells you what the operator is in Schwarzschild.
Okay.
That gives you the Lorentz gauge from the psi 4 or psi 0 in Schwarzschild.
And does it look like that can be generalized?
It looks like it could be, yeah. Haven't done it, but it looks like you could certainly guess something that would. So that works better in Schwarzschild, whereas the thing we were talking about previously, the guess we had doesn't even pass the checks of Schwarzschild. Whereas this one, you get the right file scalar, so you recover all the radiative degrees of freedom. You satisfy the Lorentz gauge equation, and you satisfy the Lorentz gauge condition.
Right, brilliant.
All constructed from the S equals plus and minus 2 Tchaikovsky scalars.
Well done, Leanne. Well done, UCD. Oh, yeah, thank you.
So I'm being summoned off. Leanne could probably fill you in more on that.
Is it congratulations to Barry?
It is. Yeah.
Yes, it is.
When did that happen?
Yesterday.
Congratulations, Barry.
So we're sitting at home. I'm at home with the kids with Capra on in the background for some light entertainment. A boy, no name yet, but boy.
Excellent. balanced. Congratulations.
Thank you.
Okay, if we don't have more comments on this topic, maybe we can go on to the next one.
I've just got a quick point about so we need H1 everywhere, and as far as I understand it, does Martin's code not give it everywhere? It's just near the world line.
So that's also true. Nobody is currently actually calculating H1 everywhere. And
So is that a limit of MST? Is that right?
So yeah, the way Martin explained it, MST is just not ideal for that purpose. And just solving the Tucholsky equation numerically would be more efficient.
Okay.
Yeah, MST is slow to evaluate. So it has many very useful properties, but it can be quite slow to evaluate when you at a given radius. If you want to then evaluate it at 10,000 radii, it's definitely not the way. You're better off maybe using MST to evaluate a couple of points and then numerically integrating to reach the other points you want, or just numerically integrating depending on the context.
So one thing that Chris mentioned or suggested was that he can output the analytical MST solution at low PN order or some PN order, and it's just an analytical function. And we could play with that as a starting point.
Yep, that's true. Can you hear me?
Yep.
Yep, that's true. But again, it's not everywhere. But it is near the particle. So if you want to play around with the singular behavior,
yes, doing this kind of regularization, yeah, it'll work for that. Okay, let's move on to the next topic then. Yeah, balance laws and evolution equation for the Carter constant. Yeah, so as we saw this morning, we now have balance laws for energy and angular momentum at second order. And so we can now calculate the average rate of change of the energy and of the angular momentum just for modes of psi4, the boundaries. We don't have a similar result for the Carter constant. So the question is, can we extend what was done at first order, so Mino's result and the subsequent work by the Japanese group, Saigo et al., and by Scott Hughes and collaborators. Can we extend this to second order? So I have essentially no ideas on that. I was hoping that Takahiro might have some good ideas. And Jordan, if he's still on the call. Oh, and possibly Beatrice, who's now joining. So do we have any volunteers from Takahiro, Jordan, or Beatrice to comment on balance laws, post-adiabatic balance laws for the Carter constant? Or anybody else? This may be a very short discussion.
So I can just offer a couple of comments as to potential routes and why those potential routes are challenging.
Okay.
So in particular, one might hope that our work with the post-adiabatic energy and angular momentum might be able to be reapplied or adjusted in some way to apply similarly to the Carter constant. And I think that there are definitely good attempts that can be made there. There's certainly a similar evolution equation for the charge of the small companion that you can write down that looks like that. And then as a separate statement for the Carter constant, there are certainly symmetry operators that yield asymptotic currents. I emphasize the plural there, that as Alex Grant has found, there's not just a single definition of current that reduces to the Carter constant for null rays in a geometric optics limit. So it's not clear precisely how that should generalize. And then most spectacularly unclear is how those currents and corresponding to those symmetry operators should correspond, if any of those particularly should, to quantities that you can derive at the small companion. And I want to point out that there's challenges there, especially associated with Alex's earlier work, where he points out this no-go theorem of a momentum conserving interaction of you start with one particle following a geodesic with preserved Carter. It splits in a momentum conserving way following two geodesics, and then those two geodesics re-encounter and merge again following a final geodesic that then again preserves Carter. Now, and despite the fact that Carter is preserved during each of those four geodesics, sorry, the Carter from the start to the end of the system is not conserved.
So how do we have a law of first order? There's this really interesting result by the Japanese group in their paper on the flux balance laws at resonance, where it wasn't actually pointed out in the paper, but it seemed like a really interesting, powerful result, where if you look at the average rate of change of the Carter constant using the formula that Sego et al. Originally derived, it involves mode amplitudes, but it also involves local information. You can't really guess that it's a asymptotic balance between something at the boundaries and something local, because it directly involves local information. It's not something you can measure at infinity. But then if you instead write down the average rate of change of the radial action, I guess, or one of the action variables, instead of the Carter constant, there it actually only involved asymptotic quantities. There was no local information in the equation. It's strictly the derivative of a local quantity is equal to an asymptotic quantity. So that seems like a potential avenue to figuring out what kind of asymptotic thing is actually being balanced here, and using that as a route to go to second order, maybe. Do we have any of the authors of that paper on the call?
Takahiro is here.
Akira is here.
I think so. Is it not?
Might have left. It's like 3 o'clock.
He is on the call, but yeah, it's unfortunately very late in Japan.
He might be falling asleep.
One can find times that work for the US and Europe, but not for US, Europe, and Japan simultaneously.
It's difficult.
So do we actually expect to have that a conserved Carter constant beyond first the linear order? I look at it from the full GR problem, as we have conserved energy and angular momentum, but we don't expect to have any other conservation. So there appears to be a miracle to do with the particular symmetries of Kerr, but is there a reason to think that it goes beyond the leading order?
No, but it's not actually conserved, right? And we're looking for its rate of change.
Balance, yeah, well, there's a balance law at first order, that's what I meant. But is there a reason to think there will be a balance law at second order?
There wasn't a reason to expect it at first order.
Yeah, but there's one miracle. That's not a reason to expect there to be another miracle, because when you look at the full problem, you don't have any symmetry that would suggest anything like that.
Well, last year's Capra, someone was talking about is there asymptotic current that could actually correspond to this thing, and Beatrice said, yeah, of course there is. I don't know if she wants to comment on that.
Yeah, I had the following reason. Because asymptotically, the Carter constant nicely decomposes into a product of vector fields, right? Of actual symmetry vector fields. And therefore, I would have anticipated that because asymptotically, the Killing tensor becomes so simple, there should be an associated current with it. That was my intuition, but I mean, I never really looked very much into detail in this problem. But maybe someone else that has looked into the mathematical details can comment on this.
So there was actually a paper by Alexander Grant and Anna Flanagan where they derived, that's what Jordan was talking about. You have symmetry operators, and these symmetry operators derive, define conserved fluxes. And what Alexander did was he took a look at these fluxes, took the aconal limit, and said, oh, so these are, somehow fluxes of particles. And these fluxes corresponded to things such as, the fourth power, the sum of the fourth powers of the Carter constants of the particles within the box, or something like that. So it's a little bit, well, it's not as straightforward as one would think, but there seems to be some kind of flux of the Carter constants in the gravitational waves, but not all of them are finite at Scry, etc., etc. And still, even if you have these fluxes, you're not sure how the Carter constant is transferred from the particle to this flux, because the Carter constant, as Jordan said, is not conserved in momentum conserving interactions. So when you conserve linear momentum, the Carter constant is quadratic. It's not conserved in that interaction. So it's a little bit complicated like that.
Is there the possibility of just trying to directly extend Mino's derivation from first order?
I would say it's very straightforward, actually, but I actually never quite understood. So if you have something which is called the radiative metric, does that mean you can reconstruct that easily from curvature perturbations, for instance, or?
not sure about curvature perturbations, but you can reconstruct it from psi4 because it's a vacuum solution. So you can always apply the CCK reconstruction straightforwardly and just express the result in terms of Tucholsky amplitudes. So that might not give you a physical interpretation of it, but I think you'd be able to get the result you need.
So I mean, like for instance, the d Carter constant over dt it's the equations that apply for it are the same at second order as at first order, essentially, right? Or at least the part which comes from the second order metric. So you can just very straightforwardly do the same thing, and you will get the same formulas, but I don't know how useful they are, right?
Huh. Is that true? Yeah, I guess you'll have quadratic terms that it doesn't work for, but the quadratic terms are easy to calculate. It's the second order piece that's hard. Maybe it is straightforward.
But I mean, as I said, you said that in the original derivation, it looks like you need local information. But I had actually with Soichiro a long discussion about this, and he said that somehow you don't need to reconstruct the metric. You're just using a part of the metric, since you are kind of using the radiative part, which is a combination of the advanced and retarded field in a particular way, right? Then you do not need to reconstruct the metric.
Yeah. So the when I said it has local dependence, that's not local field dependence. That's local dependence on the properties of the world line. So like the 4 velocity, things like that. But yeah, you don't. Yeah, that's right. You don't need local metric perturbation.
Okay, then of course that's then it should be pretty straightforward. So okay, so I recall the discussion we had with Soichiro, and it's when you recast it in the action angle variable kind of language, of course in the end it factors out into an action part times, let's say, non-local information, but you would expect that in any case, actually.
So maybe we already have what we need then.
Well, you just need the second order psi4, right? So
yeah. I always found Mino's original derivation so confusing that I didn't want to go back and look at it again. But I think the Hamiltonian derivation was much more readable. Right, I need to talk to Suichiro about that. I don't think he's on the call. Or maybe you want to just write a quick paper about it.
Sorry, do those first order derivations not assume a more direct relationship between the first order metric perturbation, the first order regular metric perturbation, and the first order radiative metric perturbation than exists for second order?
Could be.
Just by analogy to the derivation for energy and angular momentum, is that that conversion at first order was effectively trivial, and then at second order was deeply involved.
That's true. Right. Well, we should look again at at all the Japanese papers and see if there's a path that's just waiting in front of us. Okay, any more ideas or thoughts or comments on this? Zaid?
Yes, hi. So I'm just thinking about a discussion we had not so long ago about just seeing how far the effective metric approach can take us, as we did with the energy and angular momentum balance laws, just seeing what we can do with similar style derivations. So I'm wondering if that might be something to look into as well.
That certainly gives you a more compact starting point. It's not ultimately an essential part of the derivation, though.
Right.
But yeah, certainly those notes that you wrote, you do have a much nicer looking evolution equation, a local evolution equation to start from, if you write it in terms of the effective metric.
Yeah, so I'm taking a quick look now, and I already see we have two terms involving covariant derivatives of the residual field, and things already start to diverge, as you would expect, quite rapidly from the ENL case. But I'm just wondering if that's interesting to note.
Yeah, yeah.
Thank you.
Okay, if there's nothing else, what's our last topic? Oh yeah, parameter space. Out of here. Yeah, so Niels is much more optimistic about this, but the overwhelming impression I have is that second order calculations are really big and really slow. And even sampling the parameter space at adiabatic order is very difficult, just because the parameter space is huge. So the question is, are there good avenues to help us fill out the parameter space? So the talks today and the presentation I gave in the morning were very, very focused on two timescale method using frequency domain field equations. But we should probably be looking at every different avenue we can get. So I've just jotted down a few ideas here. One is obviously just faster computational methods. One would be clever sampling and fitting, or for example, going through EOB. So yesterday in the discussion session, we were talking about, would we be able to get enough information from post-adiabatic order to actually just have post-adiabatic waveforms at the ready? Or would we need to just use adiabatic waveforms or even simpler waveforms for detection and then resample the parameter space to get more information in the region where the detection was made? And I can kind of imagine doing like some kind of rough sampling or some kind of clever sampling that would allow you to include post-adiabatic information, but not very accurately. And then you'd go in and further improve your sampling in a neighborhood of the detected parameters. Another option would be, as mentioned yesterday, time domain for highly eccentric orbits. It may be time domain for any kind of orbit, but it clearly has an advantage for highly eccentric orbits. So most of tomorrow's, at least the morning session, is all on time domain methods. And maybe that's a good way to fill out parts of the parameter space. Along those lines, everybody these days is talking about using scattering orbits in order to get information about bound orbits. So the whole scattering revolution and post-Minkowski theory. Can we do that in our case? Can we calculate scattering orbits and from that, extract the Hamiltonian for bound orbits using analytical continuation and make things much easier for ourselves if we can make scattering orbits much easier to do than bound orbits. So Ollie Long is talking about scattering orbits in the time domain tomorrow. So maybe that's one way to go. Another option is Green's function methods. So what we do now is, we're solving the same field equations again and again and again and again and again with the same, or with different parameters each time, different source parameters. But, reconstructing or constructing homogeneous solutions again and again and again. But if you can just calculate a Green's function, then you just calculate it once and for all, and then you don't need to recalculate it. And so can we use that to help fill out the parameter space for second order? So maybe using the Green's function or 3-point functions that Abe talked about today. And I think that can especially be combined very well with the Detweiler stress energy formulation of the field equations, because that would give you a nice source that you could just integrate against. And also, Soichiro and Takahiro over a sequence of Capras did present something like a second order formulation using Hamiltonian. It's again based on Green's functions, but they never quite finished that work. But I wonder if that's another way to go. Then there's the possibility of doing the kind of MST post-Newtonian approximations that have been done at first order a lot, doing those at second order. So Chris is talking about that tomorrow, and we have some early promising results, albeit in a scalar toy model as usual. And then there's the possibility of just taking information from other models, from other two-body models. So just take the highest PN order available and just put that into our model. Or take EOB information and just put it in, or take even extrapolated NR data. And so there's been a lot of work in using self-force to inform other models, but we haven't really taken advantage of using other models to inform self-force. So Wojciech mentioned this as a possibility yesterday. And yeah, I think that's something that should be investigated. Anyway, this is a long list of possibilities. I don't know if anyone has any comments on these or other suggestions.
So once again, Wojciech reporting from discussions with Soichiro. So Soichiro explained to me that, well, in the work they did, and as well in the work of Nico Younes and collaborators, they kind of investigated using PN theory, and in principle, to get where we need to go with second order computations, we would have to go to like 7 PN theory, which is simply not available at this point and probably never will be.
It's not going to be available for a long time.
Yeah. So now you have like 3.5 relative to leading order fluxes, and those have second order in mass ratio pieces, of course. but yeah, that doesn't really help. That gives you like one significant digit probably to the.
But were they trying to get the entire in-spiral with it, or just a portion of the in-spiral?
So I think their criterion was to be in the Lisa band for the observation time of Lisa. So that was kind of like what they were doing. So if you have a very high mass ratio, very heavy black hole, you will you will do a few cycles in Lisa band. And yeah, so it's like that.
Leo, you have your hand raised?
Yeah, so I don't know how many of you managed to see Martin's paper from today, Martin and Harold. There's a figure 4 there that's fantastic, fantastic in illustrating the answer, or in a suggestive way, the answer to this question, where how much we can do with PN. So is the so there's this usual map of the parameter space. They were looking at Schwarzschild and the circular orbits, and there's this.
Do you have the paper pulled up on your computer right now?
No, I don't. You could maybe. Yeah, it's better than me trying to describe it. And so, yeah, so they only looked at 3.5 PN, but you could see that you can't really use that for an in-spiral.
Not even for a portion of an in-spiral?
No, not really. And well, of course, if you go to 20 PN, then you can start doing things, but then you're restricted to the extreme mass ratio only. Well, yeah. But yes, figure 4 at the end.
Good.
So this is a study of the. So there comes some comparison of essentially cell force results with the numerical relativity, looking at quasi-circular in-spirals and using a large number of numerical relativity simulations, 55 simulations with mass ratios between 1 and 1/10. And they were looking at the phase as a function of the frequency. They were comparing the sort of how well the cell force agrees with numerical relativity at the adiabatic approximation, first possibly adiabatic, and then they can extract from by subtracting it the adiabatic, post-adiabatic from the numerical relativity, they could get all the leftovers. And I'm sure Martin will talk about this tomorrow. There are lots of interesting results there, but what I want to say here refers to figure 4, where it sort of shows what the coverage in this space is of the different methods. So in pink, the small mass ratio expansion, and in green is the Poissonian expansion, and the different sort of contour lines indicates the error, the total accumulated phase error. So you see that if you do 3.5 PN only, then you don't really reach very far. You reach something like 60 maybe at large mass ratio, or a small mass ratio here. Something like 60 M. You already pick up a phase difference of pi/16.
Over what length of time?
So there are some fiducial initial frequency there, which is something like 0.22, I think. So I'm not sure what that corresponds to in terms of time. I think it's a big portion of the Lisa band in spiral.
Yeah, the reference frequency is whatever this is.
No, that's not a reference frequency. They started. Oh, is that?
Isn't it? I thought they're measuring deviation away from this frequency.
Oh, why that's 0? Okay.
If you add all the frequencies here, look
all
at
right.
the.
Well, anyway, I just wanted to mention that there's a way of quantifying this nicely. And it seems that, yeah, definitely, if you start your inspiral at 150 M, then you want to use PN, but but you have to be very careful when you use it use this in the strong field.
But he concluded in this paper that what you want to do is combine PN with.
Sure. Yeah. Well, but look at the graph, you'll see how well you can do that. And if you have if you're at equal mass, then definitely you need to use PN. So the interesting feature here is that the PN lines are slant. You see, PN does much better at more equal masses.
Yeah, well, this is an old thing, right? It was investigated quite a while ago.
I would think so, but still, when I show the famous parameter space diagram at the beginning of each of my talks, and I show this slant line, I always get the question, why is it like that? And
this by Nico Yunus investigating this like 20 years ago?
I'm not sure. You mean that the PN sum converges less well for less equal masses? Yeah, so I had this idea. I don't remember where I heard that, but this plot makes the point nicely, I think.
Yes, it's pretty steep.
Mm-hmm. So I had a question, a more general question, a preliminary question about this. Is the ambition here to cover the entire parameter space with post-adiabatic waveforms? Because maybe
I think we need some kind of sampling as a starting point, because otherwise, even just generating one post-adiabatic waveform is going to take forever.
Yeah, so I think the ambition really should be to cover the parameter space with adiabatic waveforms.
That goes without saying. We need much denser sampling with adiabatic waveforms.
Right. And on top of that, have a machine that knows how to calculate very accurate post-adiabatic waveforms for a very focused area of the parameter space to be used once you have detections as a minimum. But there should be
there's no reason not to try to get post-adiabatic information into your templates.
Sure, if you can, but I mean, if you can't cover the entire vast parameter space, there's no reason for dismay or to be nervous about this, because this is not how we're going to search for signals. We're probably going to use adiabatic waveforms in the first stage of the search, and then when we start focusing on the parameters, we need more accurate waveforms. So we should define the ambition better, I think.
I think the ambition is to do as much as we can.
Sure, but limited resources, you have to prioritize. So you need to decide in advance where to put your effort.
Well, I mean, the focus is getting any second order calculations done at all.
Right, yes. First, we need to do it to know how to do it for one single point in the parameter space. The simplest.
But certainly Niels is much more ambitious about what we can do. Has Niels left the call?
No, I'm still here, but other people have their hand up before me, so I thought they wanted to talk first.
I haven't been paying any attention to hands. Leor's is still up, but that must be ages ago.
Do I
figure out who's got their hands up?
How do I unhand it?
I don't know.
There you go. Sorry.
No, I seem to anyone with my hand up. I guess I can talk then.
Aldi had his hand up, but then it went down. How do I see the list of?
Normally, people who's with their hand up rises to the top, so it should be at the top of the list normally. Yeah, so Andrea has his hand up now. Yeah. So.
Can you hear me?
Yep.
I'm having a problem with the mic. So, yeah, I wanted to say something about this paper as well, but then Leo scooped me. But perhaps to resonate on the last point of your list in the slides, this paper, I think, is a good first step, in my opinion, to really start calibrating self-force models with an R. I mean, this is done for a restricted portion of the parameter space, but I think this paper is really the first step, for someone who really wanted to go a little bit more in detail in the last point of your list, from Adam's list. There also, I raised my hand again just because I was not too sure really what you meant by using EOB to improve self-force models, because I mean EOB models are based on approximations to the two-body problem. So you will be using an approximant to create another approximant. At this point, you can just create an approximant in the first place from the underlying two-body information, right?
Yeah, but the EOB gives a ready-made framework to do that, and it's already got information from other models in it.
Yeah. Perhaps it's.
I mean, we need to calibrate it with post-adiabatic information as well.
Yeah, but someone could just think of a resummation, say, of the phase. I'm brainstorming at the moment. I have not thought about this too much, but say an expansion of the phase, which I believe actually is what Martin and Harald did. An expansion in the phase in which you have the first terms from, say, PN, then the higher PN orders, you just calibrate to an R, of course, looking at a larger region of the parameter space. And then once you have the phase, you can maybe just put it into some evolution scheme. And that would be resumming the information in a way. I'm just saying, I'm not saying it should replace EOB. I'm just saying it could be an alternative.
Yeah, I'm sure there's lots of ways to do this.
Yeah, and that's all I wanted to say. Thanks.
Thanks. Okay, Niels, you've still got your hand up?
Yeah, I just wanted to check. So let's suppose we have, I guess, 10 or 15 years from now, the second order self-force across the parameter space.
10 or 15 years, we will have the circular orbits and Schwarzschild done.
Yeah. Let's maybe have it across the whole parameter space. And actually, to compute an in-spiral then is very rapid, right? The 2x scale expansion is just like the NIT. It's all very smooth. There's no oscillations. It takes milliseconds, right?
It's no slower than the adiabatic one.
Right. And so if you have a way to compute, a good way of interpolating the amplitudes as well, adiabatic order, then you still have that at post-adiabatic order. You don't need post-adiabatic amplitudes.
Yeah,
so
exactly.
That's all okay. So assuming you have the second order self-force, you're good. So then the key question is how much in the parameter space do you need to, how many points in the parameter space do you actually need to run? Right. So this is like a flux that I need to interpolate to like 4 or 5 digits. Right. It's not anywhere near as accurate as the first order force. So it's not as, you don't need as many points as the first order force at all.
Yeah.
And so I think that's the key question and it might be good to practice this with first order flux data and just say, well, okay, let's take first order data. I'm going to give you 10,000 points, and just how few of those points can you use to fit and then recover the rest of those points to 4 digits of accuracy. And I bet that's very similar to the amount of points you'll need to run in the second order case. And then you'd know, okay, and if you tell me that's 1,000 points in the parameter space, or that's not scary, 10,000, that's not scary. If you tell me it's 100 million, sure. I'm terrified. But I think it'd be really good to put some sort of number on that and say, I need to run the second order self-force code 1,000 times. That's not a problem at all. I don't think in 15 years time.
Definitely more than 100 million Niels.
No, a lot less.
Mm-hmm. Or that the
No,
entire
no, you're talking about waveforms. I'm talking about how many points do I need the second order flux in the parameter space to be able to interpolate the flux everywhere to four significant digits. That's all I need.
over the entire parameter space.
Yeah, maybe is it 10,000?
Yes, you have something like 7 or 8 important parameters. You've been working on two-dimensional slice cuts so far. It's
Right, so I've got spin, I've got inclination, I've got the spin on the secondary.
eccentricity.
What else is changing intrinsically?
Eccentricity.
Yeah, sure, eccentricity, yeah. So that's 5. I thought for spin on the secondary, we don't. No, because I'm just talking about how the second order calculation, right? I don't need to care about spin on the secondary for that.
Add that on separately.
Yeah. So I'm just saying for the second order calculation, don't I just need to interpolate over A, P, E, and inclination? So it's a 4-dimensional parameter space.
Wait, how many did you count?
Just the A, P, E, and inclination.
Do you not need the
and M, delta M, and delta S, I guess.
No, we can absorb delta S into the background, eh? Treat that as one parameter. We can't do that in Schwarzschild because we don't have a background to put it into. And
but then what do you mean? Solve the small spin in the big spin?
So I don't care about the small spin for second order calculations. We're saying, what do I need to interpolate for second order calculations? How big is that parameter space? It looks like it's 4-dimensional.
So
no.
Maybe 5.
P, E, inclination, spin of the big black hole.
Mm-hmm.
Mass.
And yeah, because the mass is evolving, then you have to add that as a separate parameter. So that's 5.
Okay.
Yeah, 5.
Right, but that's not what Leo just said, which is 10 or something. Like it's 5 parameter, 5-dimensional parameter space. And we know the mass of the black hole probably has a small contribution.
Yeah, I expect we can toss that in.
You have a phase as well, right? The periastron compared to some relative phases, at least one, that is intrinsic.
Does that appear in the second order flux calculation? I think it depends on that. It's all averaged in some way, right?
You do need to pick some reference phases, but you can pick them arbitrarily, and then you just need to. It's the same thing you did with Scott. You need to know the relationship between your snapshot phases and your evolving phases.
Sure, but that's not scary.
Yeah, no, it's a simple map.
So I mean, the parameter space isn't. I mean, it's still 4 or 5-dimensional, but it's not huge.
Hold on, 10 to the 5 is 100,000. 100 to the 5 is 10 to the 10. If you have 100 sample points in each direction, you already have 10 to the 10 templates.
Do we need that many? I mean, that's just gridding things up. Is there smarter ways of covering that parameter space? Is my point.
Eccentricity, I'd imagine you need more than 100.
But you need to know the flux to 4 digits of precision. I'm not sure you need as many. And you have some analytic knowledge as well. I mean, we should look into this. Is my point. It would be good to put a proper number on this and say, is it 100,000 times I could have run the code, or is it less?
Well, calculation is official metrics calculation. It tells you that you can tell the eccentricity within 1 over mass ratio times signal to noise, and that basically tells you what resolution you need in eccentricity, and it's tiny. So,
but do you need that for your second order term?
Yeah, I'm confused as to what you're trying to do. This is the adiabatic calculation or second order calculation?
Second order.
Second order.
But second order, don't you need also to have to resolve the spin individual? Is it the small spin?
You just add that as a separate term. That's a separate calculation.
Separate calculation, but it's a parameter in your parameter space, and then you have all the angles that come with it.
It's only one extra angle.
Okay, spin and angle. Is it one?
But in these calculations, you don't need to know the the angles. You only need to know the actions.
For the second order flux, you mean?
Yeah.
Well,
So I mean, the second order flux is going to be the same regardless of the value of that parameter. So
there can be some general, yeah. I guess it's a certain component of the spin that affects your flux. So there will be degeneracy in the space.
But what I mean is that your calculation of the second order flux without a spin takes the same value regardless of what the spin is. You don't need to repeat it along that dimension.
But the spin has a contribution to the flux.
Yeah, but you just calculate that separately. That's a separate calculation.
But you want to fit over everything at the same time.
Yeah, you just keep adding stuff to your grid. This is
yeah, right. The secondary spin appears at post-adiabatic order, and so does the second order flux. And you can calculate those two things separately and just add them together. I mean, you've definitely got to compute both of those things for the total model. But the key question is, how often do you have to run the really expensive second order calculation?
Yeah, I thought the question was how dense the grid should be. The template grid should be.
No, but you can do different calculations on different grids.
Yeah, not the template grid, the grid of fluxes. I mean, once we have those fluxes, as we said, we can compute waveforms very rapidly. That's fine. It's how often do we have to run the second order calculation? That's the key question, which is much less than you need to run templates because you interpolate.
So once again, it would be good if Suichiro was here, because they, I guess more so Ryuichi Fujita. So he has tried to interpolate the adiabatic fluxes for generic orbits. And they were finding it very difficult to do that without extremely high density. But of course, they're aiming for much higher accuracy because they're calculating the leading piece.
Yeah, like I say, I think if you did perform those types of calculations just with the first order flux and say, okay, but I only need to know this of 4 digits or so, precision or 3, that will really change things. And in terms of the methods you can use and how densely you need to sample things.
Yeah, so Ryuichi should already have some sense of that.
Yeah, that'd be great to know.
I would actually expect the second order self-force to scale with 1 over r to the 3, right? So you will have very different dependencies on eccentricity and things like that, semi-latus rectum. So it will be harder to interpolate, probably, no?
Well, I think if you had a second order flux, the first thing you do is factor out any behavior you already understand, like analytically, like its large radius behavior, and whatever you can from post-Newtonian order and fit the residual. So I don't think it's harder to interpolate just because it's falling off faster.
Right.
I mean, the numerical kludges work magic by just doing exactly that. With the eccentricity, they just subtract off the leading thing and fit the remainder. And somehow,
yeah, that's definitely what we should be doing here. As much as we should use as much analytic information as we can, and it's just in the deep, strong field, we're going to have to run our numerical codes a lot. So, but yeah, it'd be useful to estimate that, I think. Something to think about.
Yeah, I'd say definitely you and possibly me, but especially you and Scott and Suichiro and Ryuichi should sit together to discuss the generic adiabatic and getting estimates from that for what kind of sampling density you need.
Andrea, did you have a question?
Am I missing hand?
Yes, it's actually related to kludges. I just wanted to, so I see that Michael is in the chat. So in case I say something incorrect, his job is to correct me. But I think it's very important, since we throw around the words detection and parameter estimation, at different stages. I mean, it's true that probably there will be a pipeline where we have a detection pipeline and then a parameter estimation pipeline. But even probably to scope out the detection pipeline, it would be, in my opinion, very important to have alternatives to kludges very early on. So, just to see what can be done in the first place, because at the moment we do have, to use again the words of Albin from yesterday, we have two extensive models that can cover many parameters, even if they do some approximate things in places. There are two models, but the problem is that, and these are the numerical kludge and the augmented analytical kludge. I'm not mentioning, sorry, Lior, the analytic kludge at this stage. I mean, the two accurate ones are the AAK and the NK. The problem is that one is built from the other. So in case there are some systematic biases that, they may not appear. So it's good to know where they are there when one is trying to get estimates, even to do some detection studies, for instance. It was just this comment.
All right, can I address that, Adam?
Yeah.
Yeah, so I think you were talking about two different things. One is using kludges to do this scoping out of LISA signs, so be able to answer how accurately LISA can measure the parameters of the systems. Another thing is to use kludges for detection. And I agree that it's important to look at improving those kludges for the purpose of detection, but I don't understand why people are bothered about making the kludges more accurate for the purpose of parameter extraction studies. So my take of it is on it is different. To calculate efficient metrics, you don't need accurate waveforms. You need the waveforms to have the right amount of complexity or level of complexity, and you need the waveforms to encode in the right way the dependence of the waveform on the parameters. And so in principle, you can have two entirely different sets of families, waveform families with exactly the same Fisher matrix. Waveforms don't look anything like each other, but still they have exactly the same Fisher matrix in principle. And so that was the purpose of these kludges, to have something that is complete, so has a full dimensionality and just about the correct frequencies, so you get the correct sort of features in the waveforms, and that will basically encodes the amount of information that's encoded, and that should be sufficient for your rough estimation of parameter estimation accuracies. And I think that's still the case, and I don't see the reason for trying to make them extremely accurate for that purpose alone. So I think if you take the actual waveform, the eventual second order so forth waveforms, and do the official calculation based on that, you'll get pretty much the same answer. And you're only looking at knowing the answer, and you get a rough estimate, like a rough idea of parameter extraction accuracies is not an exact science. You want it's an estimate. Sorry, that was a long speech.
Remember Alvin saying he just wanted, if they're doing like neural network methods of doing anything, they wanted to be training it on good waveforms.
Yeah, for the purpose of detection, certainly, yes. You want to phase correctly, but
for the purpose of building detection methods, as I understood it, at least.
Yeah, well, I don't think I agree with that. You don't need the exact solution. You need all the features to be there in the waveforms.
Michael?
Yeah, so sorry to interrupt, Lior. I would say, and I can speak for Alvin a little bit here. I think we are using the kludge models in the way you described, where we are, well, there aren't that many people in the LISA data challenges working on MREs, but people who are are using the Kluge models to look at our ability to extract parameters just in a general sense and to kind of understand that overall problem. I think that the question is more with the more accurate waveforms, getting them fast and getting them ready to actually do the real analysis while still using the Kluge in the meantime to kind of understand what that undertaking will be, I guess, if that makes sense.
Yep, that makes sense.
So that's just planning ahead.
Yeah.
Yeah.
So can I just have a question for Mike, maybe? So do you have any idea what is the maximum accuracy with which you extract a parameter that you expect from Lisa? Because that would inform to how many digits you want the second order self-force.
This would definitely be, I think, a better question for Alvin. He's definitely more experienced directly in this area than I am. I think I've started to look at these types of questions and memories, but don't have a full answer to that yet. But I think we definitely expect to see them to very high accuracy. But I'm not sure I can really put a number to it at this very moment. I will say that Alvin and I are starting to look at using the GPU version of the AAK that we developed to start looking more into these questions and looking more into things like what the likelihood surface for emeries actually looks like. So maybe we can have more detailed answers in the near future, hopefully.
But we do have some answers to this question, right? How accurately from early Fisher matrix calculations with AK and AAK, and then later NK as well. The Wojciech, there are calculations of parameter extraction accuracies, and I can give you rough numbers right now if you want. If that was the question.
So that was the question, right? So if we are able to extract parameters to 5 digits, then we don't need the second order piece to more than 1 digit, for instance, right? So the question is, how many digits do we need actually of the second order self-force?
Yes,
right?
not quite. So assuming that you have an exact model, no error, you can get the masses to 1 part in 10 to the 5 or 10 to the 6.
Well, that would kind of suggest that the second order piece of the self-force is needed up to 2 digits, which is, I would say, a very tangible goal, right?
So certainly what we're doing in Schwarzschild is way more accuracy than I imagined we would actually need. But yeah, Leo, do we have a sense of how much an error in our second order fluxes will impact our parameter estimation?
No, well, that's it's something that needs to be quantified, and we know how to. I think we have the tools for that. But I think I agree with Wojciech that we don't need high accuracy at all with the second order calculation.
Yeah, I think Niels's original aim was 1%, but then for some reason we went to 1 part in 10 to the 5 or something.
As you recall, we actually wanted it to be less accurate so we could claim agreement with the first law. We were rather disappointed at the accuracy. It's too high. We wanted bigger error bars.
So if your second order piece contributes 1 radian, then over phase evolution, then it's enough to be 1% accurate, probably.
You could probably assess this by taking the 2 timescale framework and just where the second order piece goes in, put something in that behaves and just inject some noise into it and just see at what level it starts causing problems.
It's basically linear. The post adiabatic piece is epsilon independent, and the second order flux is just adding to that piece linearly.
Okay, so it's going to matter what the coefficient is then.
Yeah. it's basically that tells you it scales exactly the way you would naively think that 1% loss is exactly just a 1% loss in the phase.
In the post-adiabatic phase, right?
Yeah. But because the post-adiabatic phase doesn't scale with anything, it's just exactly that percentage off of your final phase.
Right. Right.
Yeah, this has been a very good discussion. I think we're out of the official time. Aaron, should we wrap up?
Sorry, I'm looking at my chat. I wanted to see if someone was saying something. Yeah, no, I think we're at the mark, and I think it's been a long day and very productive. So I think it's a good time to close up. So if everyone's okay with that, I'd say further discussion can move to the Slack channel. We'll also have, and tomorrow the discussion focuses mostly on new analytic methods, but I think plenty of that could also potentially apply to discussions about second order approaches. So in any case, thanks everyone for hanging into the end. Huge thank you to Adam for organizing this great discussion session. And I guess that's it. I'll see you all bright and early for me tomorrow.
All right, thanks.